name them and define them, and then make the mathematical model for them. In the solute transport, two kind of process will take place. Two important: one, hydrodynamic process, and the second, hydrogeochemic and microbiological process. We can define them. The hydrodynamic process will affect all kind of pollutants because it is physical process and it is a dynamic process. It is responsible for the movement regardless of the reactive or non-reactive. So it is responsible for the movement of non-reactive materials and reactive materials. But the hydrogeochemic and microbiological process is only for reactive process. So even you have even if your pollutant is not reactive or non-reactive, it will be affected with hydrodynamic, but it can only affect the reactive materials. Hydrodynamic process are advection, dispersion, and molecular diffusion. That we will explain them and how they can affect the movement. And hydrogeochemical and microbiological process can be solution, precipitation. This is the question that you asked about how we can model the arsenic comes from the natural sands inside your the aquifer. This is solution. When something solute water from the sediments, you can model it this part. Precipitation is reverse. If something precipitate from the groundwater into the system or from the river into the, you can model it. This solution, again like solution. Redox and reactions, sorption or cation exchange. We can list it more, bacterial or also decay, everything you can add here, which is related to the chemical reaction or microbiological reactions. We have several, at least only some of them. We can add microbiological degradation, we can add other chemical reactions, vitrification, whatever that happens as a process, we can consider them as a chemical or as a bacterial thing. We'll start with the hydrodynamic process and how we can model it. And then we will go to more others. Here is another example about a farm and a pesticide. It shows the pesticide cycle. When a pesticide comes into the field, as you remember yesterday, when and I don't know the name of the lady that she very she explained very well for us about the pesticides as she was a professional in this subject. She said that it can vaporize to the air, and she said that it is responsible also for air pollution. Yes, we can see it here also. When we add them, they can vaporize and go to the air, so they can make the air also pollution. When you breathe in this field, then you will have some of these pesticides in your body and make affect you. And also when it goes to the crops, some of them will absorb to the crop, and then the crops come to the market and we can use it again. And when it goes to the soil, some of them will leach with the rain and goes toward the groundwater. This is the leach below root zone. Some of them can degrade it by bacterial or oxidized with the chemical reactions that happen. And some of them can absorb to the soil particles and again goes, and the excess one goes to the water bodies which is related to the hydraulically connected to the groundwater, or sometimes the runoff can go to the rivers. And we have a heavy rains that is much in India, then we will have lots of runoff. So they start to wash the things that was here to the rivers. So this is the cycles that happen for the pesticide. This is the conceptual model. I told you, if you are going to make a model for pesticides transportation, this is our conceptual model. What the things that can happen for the maybe some of our important. This is second step, and we also this is not important. I don't. For example, maybe if you are going to model pesticide transport to Iran, which have not so much rain, then maybe you can eliminate the runoff. And you see, no, runoff is not an important process in here, and it is not necessary to model it. Or maybe your soil characteristic is in a way that there is not so much adsorption, so you can eliminate it. You should, at first, you will nominate all of important process that can happen, and then you list them from most important one to the less important one, and based on your time, your facilities that you have, because when you add one reaction, then it needs time, it's specialists and everything, because we need to calibrate. All of them are different models. You should calibrate them separately and then make a complete model to solve your program. So these are the process that we can consider in total. But now we are going to advection and dispersion. Here is not very clear. This is an experimental setup that we are working on it now, and we inject through this pipe into different part of the groundwater to see how solute transport. The water table on the upstream is here around 10 centimeter, and downstream is 4 centimeter. And this setup is made ready for capillary fringe and to see how movement in the capillary fringe. But here we injected in the saturated zone because this is the groundwater table. This black line is the groundwater table, and you see this green part. It's not very. Can we make switch off this one? This is more clear. Yeah, this. None of them. Okay. Is there here? There's behind the. Yes. One second, you turn off it. Yes, but it doesn't change so much. This is the green part. You see the circle, which is green. This is the place that we injected. And if there is no dispersion, because the velocity is in this direction, we are expecting that this circle start to move from here to here. But in reality, when we make it photo, it's not again clear here. But you see that this green part is something like here. And because we have two processes that affect the transport, one advection and one dispersion. Advection is responsible to bring it from here to here, but dispersion make it wider. So this is why the green part is like this, and the do you see this or not? And the green part is clear also. You see the green part, the end is here, and the start is something here. So it expands. In the next one, I should eliminate this part, and it is more clear. So when we inject here, it starts to move from here to here. The center completely moves and come to the other part. This process that the cloud from here moved to here is called advection. If I redraw it here, then maybe it's better. You know, we injected here like this, and then after 10 minutes it becomes like this. From this point it starts to come to here. The center is here, and the center is here. So we have a movement of the center from this part to this part. This is called advection. and it is related to the average velocity of the groundwater system. And it is like when you put a stick inside the river. When you throw a stick inside the river, you will see that it starts to move. If you pour a pollution also or color into the river, again it's happened to it. It starts to move from one point to another point. This is advection, and the main factor which is related to it and which is moving the cloud from one point to another point is velocity and movement of the water to the system. This is called advection. But if the only process in the river which is responsible of the movement is advection, then we should have something like red one had. If there was only advection, when you put a stick inside the water, only advection work on it. So the wood from one point comes to another point. But when you pour some color inside the river, you will see that it moves and it starts to become bigger and bigger and spread. So it shows that another process take place and another process is responsible for it. This process consists of two processes. This is not only one process. Diffusion and dispersion. And there are two different processes that happens. But we usually in numerical modeling make them one, and we consider as one process. Usually in the advection dispersion models, we don't have two terms. One term for diffusion, one term for dispersion. We consider both as one term, and we consider a coefficient for them as one coefficient. In next slide, I will go more details about this phenomena, because this phenomena, the advection is easy, and also the modeling of advection is also very easy because it is related to the average velocity. The average velocity, you have the average velocity, so you can calculate how long it will move. If you have the velocity of 2 meters per second, so after 2 seconds, the cloud moves 4 meters. Yes. If the velocity is 1 meter per second, after 1 minute, it will go 60 meters forward. So it is easy to model the advection. It doesn't need any. But dispersion is a little bit different. Why it start to spread, and what is the formulation for that? Again, we have to understand the difference between the diffusion and dispersion. We will have another movie here. I take it from YouTube. You can also, if you search diffusion, you can find several movies like this. This is two beakers. One of them is hot, and one of them is cold. You see the temperature here. You concentrate. After I start the movie, you can concentrate on it. You see this temperature is low, and the temperature in this is higher. Okay, so it is hot and it is cold. Then this man put two drops of pollution in both, and there is no movement inside these beakers. But you see, in the A, it starts very fastly dispersed into the water, but in the cold one, you see it doesn't move so much. It's very slow. But even in this one, if you wait for a longer time, after a longer time, it becomes completely red. But the A, you see, already becomes completely red. The main reason for this phenomena is diffusion, and it is because of the Brownian movement of the molecules of the water. The molecules of the water have movement, and this movement is start to help the pollutions spread in the water, and the governing the force which do is a gradient concentration. The color move from the place that has more concentration to the place that has less concentration. So it's related to the gradient of the concentration. If the gradient of the concentration is high, so the movement is faster. It means that when you inject the drop, the drop is 30 ppm, and you have a drop of 100 ppm. The drop of 100 ppm is faster than a drop of 3 ppm because the concentration gradient is much more, so it is faster. So start to, you see what happened here. So how can we model this diffusion phenomena? We will use the Fick's law. It has two. Fick's law has two parts. The first Fick's law, it says the diffuse mass, which is kilogram per square meter multiplied by second by time, is minus d multiplied by rond c divided by rond x. Rond c divided by rond 6 is concentration gradient. It means that if the concentration gradients increase, then the diffusive mass flow will increase. So this is the example that I told you. If we have a drop of 30 ppm and a drop of 100 ppm, then the drop of 100 ppm is faster because this term concentration gradient is more, because 100 minus 0 divided by x, but in the first example it is 3 minus 0 divided by x. So the concentration gradient is much more, so it's faster. And this d is diffusion, molecular diffusion coefficient. So this is the one. This is the first Fick's law, and the second Fick's law, if we want to use it to see how concentration change in the time, would be this formula. It shows the change of the concentration in one point with T would be D multiplied by the second order derivative of C regarding the X. And D again is molecular diffusion. Molecular diffusion coefficient, and the molecular diffusion is related to molecular weight of solvent, medium in which diffusion occurs. You see, if the temperature is higher, then it's faster, or this is, and also if it is oil or if it is water, you know, there are different things. If you put a drop in honey and put a drop in water, the dispersion is of course it would be different. So the medium would affect the results. The temperature affect the porosity and of the porous media, of course, will affect it. If you have a soil like clay, and if you have a soil like sand, of course it's affect the movement. And also sorption capacity. If we have sorption, I mean if the pollutant that you have has a sorption characteristic, I mean it can absorb to the soil, then the diffusion will change. If you, this is so we already reached to our mathematical model for diffusion. This is the mathematical model for the diffusion. We already go one step forward. We define the concept and we define the physical problem, and now we have the first part of the solute transport. This is the diffusion. Yes, we have X and T. So we can see in the medium in different X and in different T what happens. So if you solve this problem, then you can understand how the solute transport inside the river. I hope that we can have time, and I teach you how you use it in the MATLAB to solve this equation, this very simple equation. This is one numerical model that one of my students have done for his CFD course, it is their exercise that they should do. They solve this example. This is a river, 100 meter length. In the middle, we inject some pollutant, and it is 100 ppm, the red line. Okay, the red line is 100. So it is a box. In you see, this is 1 meter. The question was the question was this: if we have a river of 100 meter, and we add some pollutant into the river, which has a width of 1 meter. I mean that 1 meter of the this river become polluted with concentration of 100 ppm, and this river there is no movement in it. In this example, it is constant. How the pollutant start to move from different part? Of course, the concentration in the middle start to decrease, and from right side and left side it start to move. Yes, because the total mass is constant. So if when it start to goes to the right side and to the left side, so the concentration start to decrease. So you will see after sometimes it becomes like this green. You know, this green has a little bit wider from, so it start to move. And after another time at the end it reaches to here, and the width is become here. If you let it time, then it goes completely, and the concentration in total medium becomes constant, and because it's dissolved completely. Again, here you can do the validation for your numerical model, even if you don't have any data. What is the validation here? You have the river, okay, the length of the river. You have the width of the river, okay, and you have the depth of your river. So you have you know how much water is inside the river, okay, and you know how much concentration you add to it, and you can calculate if completely become dissolved to the water, how much would be the final concentration. For example, we have 10 liter of material with 1000 ppm, yes, and we add it to a pool which is 3 cubic meter. You can calculate what is the final concentration from basic chemics that you have. We had C1V equals C1V2. Do you remember in the chemistry? Or yes, have this formula for calculated, so you can calculate. So you can see the final concentration of your numerical model to see is it equal to this or not. If it is equal, so it is valid numerical model. It's modeling, theoretically model well, but maybe it's not very practical, but theoretically it works. So it needs calibration to work. You need to calibrate the dispersion coefficient or diffusion coefficient. We assume a diffusion coefficient here. So this is the diffusion and effect of it on the solute transport with a numerical model. This is a practical part. Again, I bring it from Gilham. This is a book. It's a very good book in solute transport in the soil. We want to see how much diffusion is important in the groundwater system, because in river diffusion is not very important, because the velocity in the because we have advection and fusion that are working together. The speed is very low. If it is zero, the only factor is diffusion. But if you have a velocity of 2 meters per second, then diffusion is not very clear. Is it opening or not? Is it working or not? He said that if the velocity is 1.6 multiply is less, if the water velocity is 1.6 multiplied 10 power minus 10, then the molecular diffusion is the main factor affect the solute transport. How we can understand it? From the diffusion coefficient. We know the diffusion coefficient, so we can understand how much speed we need at least that diffusion be the main process, not velocity, because usually advection is the main factor which moves. So he said that we're considering it, and if we assume that hydraulic gradient in a groundwater system is 0.01 meter per meter, which is a maybe around average groundwater hydraulic gradient. It is a little bit high even. And the porosity of 0.4, this would be correspond to a hydraulic conductivity of the order of 1/5 multiplied 10 power minus 8. So if you have this hydraulic gradient and you want to see when this velocity happens, so you need to have a hydraulic conductivity of this part. And if you go to the clay mineral have 5 multiplied 10. It's less than this. So it is something that can happen in the natural condition. If you have a groundwater which is clay material and the hydraulic gradient is around 0.01, then what will happen? The diffusion is the main factor for movement of the solutes inside the river. Okay. As you see, the diffusion has very small amount of a small amount, and it expands very slowly. And it is only very important that the velocity is slow. But when velocity is increased, and you go to a river and you look at it, you will see that the cloud expand very faster than we expected from diffusion. I mean, when you put the water constant and you put a drop, you'll see you will see how is the speed of the growth of the cloud. But when you look at a river that you put the pollutant, then you will see that it expands faster. So there is another process that happens which make the cloud faster. This is not diffusion. We call this one dispersion, and the dispersion is happened because of the velocity and because of the turbulence that happens, and the shear between the layer of the water, exchange between the layer of the water, where when the water start to move, they start as a layers, and they have when we have a turbulent flow, we have exchange between the layers, and these exchange and these things make the cloud become spread faster. So when we have the speed and we have the movement, then we have another process called dispersion, and it makes the cloud faster become bigger. But when we're going to modeling for the dispersion part, we only consider the same factor, and usually in the solute transport books, they consider this D as a dispersion diffusion coefficient, and it is equals diffusion coefficient plus dispersion coefficient. I mean, we consider one coefficient represent both of them because they're the same more or less. I mean, the mathematical form of them are the same, so we can make them as one and consider this coefficient as dispersion diffusion coefficient. But it is important that you know that there are two concepts. Diffusion is different by dispersion. The main driving force for dispersion is the velocity change, but main governing force for driving force for diffusion is molecular movement. So there are two different concepts. Here we have the we are developing our pollutant transport model. Now we have another term. This is advection. So this is the complete hydrodynamic solute transport. Do you remember we had two kind of process? One hydrodynamic process and one geochemical process. Now our hydrodynamic process is finished. It's a complete advection dispersion equation. And if somebody asks you what is the governing equation for solute transport, then you will say this one, advection, dispersion. Of course, we will add some other things, and it is from that now it is easy, because we had plus, again another thing, plus another thing, and sometimes we have plus only source and sink, because some of the things will add the pollutant and some of the things decrease the pollutant. So it is, if it is positive, then it's add some pollutant to the system. If it is negative, it is sink. And so decay process is a sink. Yes, sorption is a, again, is a sink. But if you have a well in some places that they are adding pollutant into the as you say recharge place, that they are adding some pollutant again, so it would be working as a source. So you should consider in your model as a source, and it will add here plus that parameters that are added. So from now it would be easy. We can add something, or we can eliminate something from it. This is our previous example. We had 100 meter. Now, because we want to make it more beautiful, again, it is from my students that he had it as an exercise. We consider 20 meter of place becomes polluted to 100 ppm. This box, this is the initial condition that we want to start to solve the problem. And when we consider advection and dispersion, you will see in different time steps what happens. This is the first one, second one. In the start, the peak starts down and it starts to increase. This is what we see in the movie. It starts to move and start to. Do you remember in the movie? It starts to become long because it's dispersion affected, and the movement from here to here is velocity. For example, if you get the x here, okay, and you get the x for this curve again, the maximum, you can calculate the delta x, the distance between the them, and you have the time step of this and you have the time step of this. If you divide delta x by delta t, then you calculate this u, then you will reach to this u. So do you remember I told that we can calculate velocity with the tracer study? You, I think, asked me, yes, you asked me about how can we can ask me how we can calculate the velocity from tracer study. And we can do it like this. We inject from one point and you get the change of the electrical conductivity in another point. So you have the peak, and you know when it reaches to the peak, and you have the distance from this point to that point. So you have the x and you have the time. I injected at 10, and after 20 minutes the peak reached to that point, and 1 kilometer is the distance. So I have the distance and I have the time of the transport, so I can calculate the v, the velocity, and this is the velocity of the system. And okay, so this is the main hydrodynamic process. Now we go to hydrogeochemistry process. Do you have any question regarding to this point? When you have no question, it has two meaning. I hope it is the good meaning. The good meaning is that you understand completely, and the bad meaning that you understand nothing. Because of that, you don't have any question. But I consider the good meaning. Till now, we answered, we have a mathematical model for two important high dynamic factors. One of the important process in solute transport in the rivers and in the groundwater is sorption. Some of the pollutants like heavy metals, phosphor, pesticides, they tend to adsorb to the soil. Especially the pollutant which is positive, they because soil surface are usually negative, so they absorb the pollutant to themselves. So different process, exchange, and everything. The pollutant which absorbs to the soil, there is no, it is not no more a solution, so it doesn't move, and the concentration will decrease in the groundwater, but it is in the soil now. It is not into the groundwater. So when you are going to modeling the transport, the solute transport, you should consider this. You should consider this process. So we are seeing the adsorption process. What happened? We have also ion exchange. Sometimes the ion change. We have here A and B, and we have here A, but the B will replace it. B was in the water. Some of the ions from the water soil will be removed, come into the water, and some of the ions from the water will go inside the soil, and it is ion exchange. Sometimes it's simply absorbed to the soil, and sometimes it absorbs, and then you saw this is adsorption, absorption, ion exchange. There are three different meanings. In adsorption, it's only go and near each other, and they are connected to each other. But but in absorption, it's completely goes and become some part of the sediments, and it's harder to remove it further. Again, you see the absorption process here. Sometimes it is irreversible. It means that when it absorbs, it's finished. Never it comes back again to the water. Sometimes it is reversible. It absorbs and again come back to the water, and it is dangerous because I can tell you an example from one of the beaches, not bays, in the England. I don't remember the name of the paper, but when I was studying my PhD thesis, here on that bay it was very polluted, and they sent a lot of heavy metals inside that, and the water was really polluted, and the sediments was polluted. So they start to make very hard regulations, and then don't let the factories send their pollutions inside the river. But it was interesting that after 20 years, still the water was polluted, because pollution from out doesn't come, but the sediments was polluted, and through tides the water goes high, the sediments were moved, and they start to release, because now the water has less cadmium or less any heavy metal, so now it is dissolved, start to reverse and come back again to the water. So this is why when we make pollution, it's really dangerous. Even when you decide not to make polluted, then it takes a lot of time that you get rid of these pollutions, because the sediment absorb them, and after that they will release them and make it hard to remove them. In the soil, we know that it's very important, sorption. When you are talking about the groundwater, it's important, because the main medium is the soil and is the ground. So of course we have a lot of sorption, but even sorption in the rivers also important. In river sediments as suspended material, as SPM, is the third important pollutant in the rivers. The first important pollutant in the rivers is salinity. The second important pollutant is nutrient, and the third one is the sediment. So sediment is one part of important things inside the river, and even the ground of the rivers are soil. Again, at the bed of the rivers we have a lot of soils. So when we add pollutants into the rivers, these pollutants, they can absorb to the suspended materials, and also they can absorb to the sediments. So in the pollutant transport in the rivers, also sediments play an important role. And to prove for that, we bring one table from Huang 2007. He had some studies, and he has a table in his paper. And you can see that in different rivers, in US rivers, in FRG rivers, and in Rhine River. Okay, this is the three river, and this is the metal. And for example, in the US, 76% of the chrome is in the sediment of the river. The total chrome, if we calculate the total chrome pollution, 24% of the total chrome, which is in the river, is in the water, and 76% of it is in the sediment. And you have, for aluminium, 98% is in the soil. So you can see that, and for example, for cadmium, we don't have any data for US, but we have for this river 30%, and for this one 45%. It shows that how much important is the sediments in pollutant transport, even in the rivers. So in the groundwater system, of course, is much more important because the main part of the medium is the soil, and absorption can really happen. So we must, when we are going to modeling heavy metals or phosphor, which have this affinity to absorb to the soils, we should consider them when we are trying to model. We cannot only use advection dispersion to see how cadmium transport into the river. Here is an experiment that they usually done to show how solute transport affect the how sorption affect the heavy metal transport inside the river. If you inject, if you consider a column, okay, and you inject from down two kind of material, two kind of solutes, which of them reactive and which of them and one of them non-reactive. I mean, one of them can absorb to the soil and one of them cannot absorb to the soil. Then when you start to inject, you will see that in the outlet you will see the non-reactive faster than reactive. I mean, at first, if you inject both of them together, but when you detect in the outside, you will see that the non-reactive reach there faster. This is because of the sorption process. And if you calculate the non-reactive speed and reactive speed and divide them together, you will reach to a factor which is called retardation factor, because the sorption retard the movement of the solute or pollutants, and we call it retardation factor. I will talk later about it when we are going to discuss about how, because now we are only talking about the process. We want to see which kind of process we have. In the next step, when we go to more details about how solute sorption affect the solute transport, then we will discuss more about the equations and these things that we should consider them. Here it has VI. See, VR is the velocity of non-reactive and VI is the velocity of the reactive. And again, for measurement the velocity, we use the same concept as I told you for measuring the velocity in the rivers. Do you remember? We inject from one point and we have the delta X and we have the time that it reached to there, and then we can calculate the velocity. So again, for both of these, you have the curve. So you can calculate, and you have the length of the column, and you can calculate the velocity. If anybody don't understand how we measure the speed, tell me, and then I explain more. Everybody understand how we can calculate the velocity of the movement? Yes? This is an example, and the retardation factor is 1.3. Because here we did some experiments and we write the numbers and it's the speed. Another factor that can affect the transport of the pollutants. Oh, I should do that. Transport of the pollutant is microbiological degradation. We know that in the environment we have a lot of bacteria which lives in the medium, in the soil, in the water, and of course they degrade some part of the pollutants. They can affect some pollutants, and they can affect and sometimes they have no effect on some other pollutants. But if you are studying for example cadmium or nitrate or other things, you should know if any bacteria can affect it, and if it affects, how is the process and how we can model this. So if you go again in the internet, you will see a lot of studies that study the microbiological degradation, and they try to model this. And of course it is a function of the concentration of the pollutant. It is a function of temperature, and also if that bacteria is on that place or not, and all of these things, it will affect the happening. There are different bacteria, and before that, and we have also chemical reactions. I didn't make a slide for that, but of course we have chemical reactions. Some chemical reactions like precipitation, and some like denitrification, and these processes also can take place, and we should model them. And usually these chemical processes, along with sorption, they decrease the concentration of the pollutant. They decrease it, and this is the self-purification. You know, if you add a pollutant into the river, it starts to move. Advection has no effect on decreasing the pollution, but dispersion, because it started to make it wider, so dilute it. When it's diluted, then it is less concentration. Yes, so this is the first factor. Maybe I show it in the second in the slide. So the dispersion and diffusion itself make it decrease, because the main one, do you remember, it was bigger. The main, when you add, it was 100 ppm, but because of dispersion it's come lower and lower because it's increasing in the vis, so the concentration decrease. Sorption and desorption, again it increasing because it absorbs the pollutant to itself, and the bioavailability will decrease, because the pollutants are bioavailable when they are in the ground, in the water. When they are absorbed to the soil, they are not very bioavailable. So they don't affect us, and they are in the soil. Of course, it is bad because, as I told you, again they can come back. It is not a good news, but at least in the water you don't have pollution. So this pollution will decrease. Even when chemical reactions happen, again they degrade the material, and it's increasing. And if biological degradation again happens, then it decreases. So it is natural attenuation. It means that when you add pollutant to the river, to the groundwater, it usually decreases and it becomes lower. In river engineering, we called it self-purification. Each river has self-purification processes. So sometimes, if you see in many years ago, when the number of the people was less, we have less industries, river was main resource of drinking and also wastewater. The people wash the things there, and some other people downstream they drink, and nothing happened. Because of these process that happens, it diluted. But nowadays, if you drink from the river, you will become sick very fast, because the number of pollutions is much more than the self-purification capacity of the river. Yes, it is like if you have a small pool and you add only a glass of dye in it, nothing happens. It becomes clear. But if you have a bigger 10 liter and you add inside, then it becomes completely red, because it is more than the capacity of the pool to purify this pollution. So we should This is one of the other advantage of the numerical modeling. With numerical modeling, you can plan, predict the self-purification capacity of the river, and you can also give some plan to decrease. I mean, you can give plan to the if you have different factories, maybe you can give them plan. For example, say to this factory, you save your you release your pollutant at 10, you release your pollutant at 12, and maximum concentration for you should be this one, to control, to have always you have a balance concentration inside the river. And now with this that we said, we can again have a flashback to the effect of the climate change. If the climate change decreases the discharge of the river, now you can understand how can affect so much the pollutant transport, because then the self-purification capacity decrease very high and the discharge decreasing. Or if the increase again, if the temperature increase, this process will be affected, and all of this together can combine and make the and then we can see how would be the effect of the climate change on the solute transport. But now to sum up about the process, because I think the we have another slide for the process for the river. For a river, when pollution comes, again we have biodegradation, we have sorption, we have volatilization, which means that the pollutant goes to the air directly from the river. It can vaporize and go out. It depends on the pollutant. Some of the pollutants have this capacity. We have bioaccumulation. Some of the pollutants can be absorbed to the fish and to the body of the fish and other animals, and then in this way they comes out from the river. Yes, they are indirectly again come to the humans, but it is not inside the river anymore. So we are going to model the movement of this pollutant inside the river. Then you should consider it. We have suspension and sedimentation and suspension. Again, it affected, because in river it is different with the groundwater. In groundwater, when the pollutant adsorbed to the sediment, then it start there and don't move. You don't need to model it anymore. You put it away and you look to another part. But in river it is not like this. We have always suspended sediment. And if the pollutant adsorbed to this suspended sediment, yes, the concentration in the river decreases, but the pollutant transport continues, because this sediment itself moving and bring the with themselves, and in some places will be sedimentated. And when it's sedimentated, on that place again we have that pollution, and we should see when it comes back again to the water. It depends on the temperature change, pH change, and a lot of other things that will affect the desorption, because the desorption is also important. We have sorption and we have desorption. We should also model the desorption when the pollutant again released to the groundwater system. We should also consider this part. Also, it is another term. Now it is sink. It is source of pollution, because sediment also can be a source of pollution, because it can release the pollution later. Yes. Now I can summarize about this process, and then I will go to other mechanical hydrodynamical effects. We talk about two important hydrodynamic effects, but we have another effects which is not directly hydrodynamic. It depends on the other parameters together and make a new effect, and we should consider them when we are going to transport them. They are not chemical reactions, and they are not like advection and dispersion, which is directly affect the movement. But however, we had several process can affect the solute transport. But we should consider two important sentences. One, all process is not responsible for all pollutants. Yes? So it is not necessary that when we are going to model, we model all the process, because each process, each pollutant would be affected by some of this process. This is the good news. So it is not necessary that we consider all the process which is in the world. We should consider all of the one who is responsible for the desirable pollutant that we are going to model. The second part, all of the process which is related to this pollutant is not have the same importance. Some of them are maybe 3 or 4 of these process is responsible for 90–80% of the movement. So you can eliminate the others. You can forget about the others, and you only consider these 4 important process. So in choosing and selecting the process, we should consider this, and then we choose the factors, and then we can use into the model. Because it is important, when you add one process, then you make the process very slower. When the model runs, it's really become more slower, because he must do another calculations, and the calculations becomes harder and harder, because the equation itself also become more complicated, and the instability and these things, which is really, because models also have a lot of complication, and it is not the time that we can talk about all these details, like stability and having reasonable results, and all these things are become complicated if we want to talk about all of these things. Another parameter is homogeneous and heterogeneous. If your groundwater be homogeneous, these models that we are talking till now is when the medium is homogeneous. But you know that under the ground it's not homogeneous. We have layers of clays, layer of sands, and a lot of things, and make everything complicated. And this is why we usually cannot model groundwater system easily with deterministic methods. And for that we are going to a stochastic deterministic method. We add some probability inside the things, and then we can see some more reliable. We assume some instabilities. Yes, of course, we don't know what is underground, but we can make some, because underground is also random, so we can make some random values for the. For example, we can randomly, if we have a medium of our hydraulic of our aquifer, then we can, for the instead of putting a same hydraulic conductivity for all medium, we can make hydraulic conductivity randomly. For one part we will give one hydraulic conductivity, for another part we will give another hydraulic conductivity, and in this way we can predict these things, because when it is homogeneous, advection and dispersion will take place very beautiful. You see, this is the advection and dispersion that we are talking about. But this is when it is homogeneous. But when it is not homogeneous, we will see something like this. And it's strange, because here we had a very low hydraulic conductivity, and the water cannot move. It can move only like this. This is why I am telling you, when we make grids, you know, do you remember we discretized the system? Then for each grid we can randomly give we know the hydraulic conductivity, because when you have your region, you have the minimum hydraulic conductivity, and you have them because you get samples and you measure the hydraulic conductivity in your field before you want to do the numerical model. Then you have different values. There are some algorithms that produce random hydraulic conductivities. So you have the minimum hydraulic conductivity of your medium, you have the maximum hydraulic conductivity of your region, and you make a grid. Now you make random hydraulic conductivities between these two values in different parts. Then you will get the results. Then you can check with your observation and check these and change this factor until they become similar. In this way, you will use some stochastic deterministic modeling. It's between them, because for your hydraulic conductivity you are using stochastic to produce the hydraulic conductivity, but you use a deterministic model to use this hydraulic conductivity to model the transport of the solute transport. You have a question? No? I will show a picture here. You know, here we have a sand. Sorry. You see, we have different layers. When you see the thing, we have a layer of clay, stones, and different things. So when we start to inject, the movement would be like this, and it is not similar to advection dispersion that we see. It's because of the different layers that we have, and in each layer we have different systems. But about the layer we have less problem, because usually when you do modeling, you usually have a geological study before, so you have somehow the geology of the region. You know what is the main layers. So you have the main layers, but inside the layers again you have some random change. That random change can take place with stochastic modeling. Okay, this is effect of homogeneous and heterogeneous. Do you have any question till now? What time is it? Did you calculate the water indexes? No. Calculate it and check if it is if you have problems. It's easy. You get some data from the internet, and then try to calculate it for one river for India or for wherever you want. Okay, another important factor is capillary fringe inside the that I talk about it. I will show you the pictures. When this pollutant start to come into the soil, I told in the previous slide that we usually assume that in the vadose zone, before reaching to the groundwater table, the pollutant goes vertical till reach to the groundwater, and after it reaches to the groundwater, it starts to move horizontally. However, there was in the literature some claims and there's some observations that in the capillary fringe we have a horizontal movement. I mean that before we reach to the groundwater table, here also we have some movement. So if you use classical models for modeling the solute transport, they forget to consider this effect, and they consider only till here, and they goes to here, and it is completely different, especially when we go to chemical reactions and biological reactions. Why? Somebody can add a process. Why, if the solute moves horizontally in the capillary fringe, then it's very important.
Due to gravity.
Hmm?
Due to Earth's gravity.
Gravity? No. Yes, the gravity is affected because the gravity will make the solute goes vertically downward, but I don't talk about it. I say that in the capillary fringe, instead of going downward. When it reaches to the capillary fringe, it starts to go horizontally. I think I have a picture. Yes, here. You see, in the classical one, we believe that if you go to the books that they show solute transport, you will see you don't see such a thing. You see that the pollutant comes here, and from this cloud is here, is like here. I mean, you don't have the cloud here because this is the water table. So in the classical modeling, they don't usually check here, but you can see that the most of the pollutant now are moving into the capillary fringe instead of groundwater. So yes, one of them is that in the previous time you think that the pollution is only here, but the pollution is now higher. This is one point why it is important. Yes, of course it's important.
Partially saturated.
What?
Capillary fringe is partially saturated.
Oh yes, in the capillary fringe, we are partially saturated. But why it is important? When it is partially saturated, what happens? What is the difference between the groundwater?
Holding capacity.
What?
Holding capacity.
Holding capacity. No, I mean, what is the difference between the saturated zone and capillary fringe? There is less water. Yes, there is less water. In this, less water than the groundwater. But what is more into the capillary fringe? Porosity and air, and oxygen. So it can affect.
So pressure? Pressure?
No. When we have air more, what can happen? When we have more oxygen, when we have more oxygen, what will happen?
Diffusion.
What?
Sir, we have more oxygen, then diffusion is more.
Diffusion?
Yeah.
No, this is not related to diffusion. We talk about a lot of things. Only why you're talking about diffusion? We have. But at least you go one step forward than the others.
So maybe chemical reactions.
Chemical reactions, yes. When we have more oxygen, of course, some oxidations and these things can take place more, and also some biological activities. So the whole process will be affected, especially when we are modeling the reactive transport. Non-reactive transport, the main change is that before that we think that here is no pollutant, but it is pollutant, and it is also very important because it is here instead of here, and it's less diluted also because it's it's up, not down in the groundwater. So this is one topic. So this is important and we should consider it. This is our experimental setup that I show you, and we try to see how is the movement of the water inside the capillary fringe, and we try to measure the velocity in different depths. So we made with these tubes, we inject in different depths, and then we measure the velocity. You see the water table is here. It's not here. It's here. The water table in this picture is here, and we inject in different parts. And it is very surprising. After you take photos, we put this is uranium that we are injecting here, and we send UV to it. Then it is more clear when you make a photo. And we make photo in several time intervals, in different time intervals, and we see that they start to move. And when they are more close to the groundwater, the speed is higher, and when they are far from the water table, then the speed is lower. And here is an example. You see, we inject the green dots shows T equals 0 when we start the injection, and each of these injection show 20, for example, here this black line shows 26 minutes after injection. This black one is 19 minutes after the injection, and this black one is 9 minutes after injection. You see that here after the injection we have a horizontal movement, and here after injection we have a upward horizontal movement, and here after 26 minutes there is no movement. Therefore, the capillary fringe has 3 layers. The capillary fringe have 2 layers. In total we have 3 layers. One saturated, and the capillary fringe is 2 parts. In the first part we have movement, and in the second part, at least during our experimental time span, we have the movement. Maybe we have a small movement, but we need more time. But in our time span, which is 5 to 6 hours, in this 5 to 6 hours, we didn't see any movement here when we injected. And if we want to, this curve, can you imagine what is this curve? But this is not your fault, because I didn't write anything, but I want to see from the shape of it. Do you think what is this curve? No, this is the water content. The curve of water content in different depths. Here is this saturated water content, and here the water content decrease and reach to a very low value. You can see that here the water content here is very near to the saturated zone, and from this point to this point suddenly it decreased so much. So we have, even from the water content curve, we can understand that we have 2 region at least, and this region has no movement, and this region has movement. I bring this water content curve to show that even from the water content curve we can understand which region we have movement and which region we don't have any movement. Oh, I should say a lot of things here. Our aim in this research was to see how is the velocity change inside the capillary fringe, and we try to model it also, and check check if the models which is already exist for groundwater can see this or not. I should say that this is not a new. If you use Richard's equation, then you will see the movement inside the capillary fringe, because there is a theoretical reason behind it, and this theoretical reason was well known from several years ago. But the problem is that when you are using numerical model, we usually don't, when you want to model a groundwater table, you usually don't use the unsaturated model coupled with the saturated model. We usually, when you do 2-dimensional modeling from top, then the numerical model don't consider the Richard equation. They only consider the groundwater model. Okay, because of that they don't see the effect. But if you come to the FEFLO and use a vertical domain, I mean 2-dimensional and vertical, and say to it that consider the model unsaturated, and it uses Richard equation, then this kind of thing is well appeared. I mean, it can understand that there is a movement in the capillary fringe. So from the theoretical point of view, there is no problem in the equations. If you use the equations, you will see this movement. But this is in the practical part. When you are going to the practical part and you want to model the groundwater, you will eliminate this Vaduz zone, and this capillary fringe, and you don't use Richard's equation because you believe that the pollutant comes down and it reaches to the groundwater and how it moves. Therefore, you don't look at the vadose zone. Otherwise, if you use the theoretical part, then it will be seen, and there is no problem with the models. I mean, the models that we have now, it's not something new that we are adding to it. We only try to more focus on it and to give information that there is it. And it is a start. I mean, we have some articles also for 20 or 3 years ago, 200 or no, 20 years ago, 20 to 30 years ago, that they said that we have a movement in the capillary fringe in the horizontal direction. Okay, so here we have the velocity in the capillary fringe, and it is 0 here. It shows the groundwater table. So if we go from the groundwater table higher, then we have different velocity. And from the experimental data, you can see that clearly when you go far from the water table, the velocity decreases, which is understandable. But why? Why? When we are going higher from the groundwater table, then we have a lower velocity. You have no idea? Okay, I will say something that it will help. When we are going from the groundwater table higher, what will change? You know, our energy is approximately constant, but I am not sure about it because we need more research. We are continuing our research about this, and we need some more tools to say if when we come from down to the high, if hydraulic gradient changes or not. But we are assuming that till now we assume that the hydraulic gradient is constant and it is equal to the hydraulic gradient of the groundwater table. So we assume that the driving force is the same. For example, if here we have 1 meter of water table and we have half meter here and the length is 10 meter, then we have 0.05 hydraulic gradient, yes, meter per meter. And we assume that this and this is the driving force for the movement of the water and the pollutant in the groundwater. We assume that this hydraulic gradient also is responsible for the movement in the saturated zone. But even in the unsaturated zone, and even in the saturated zone, also the hydraulic gradient in the whole part is not the same. I mean, from, you know, I assume it as a line, but if you see the water table, it's not directly a line, it would be a curve, and so it shows that the hydraulic gradient is not constant into it, because, you know, and the reason, it's a very clear reason. From here to here, the area is decreasing, yes. So the velocity will increase, and when the velocity increase, then the hydraulic gradient is not constant. It will change because V equals K multiplied by I. So when V increase, so I is also increased. So I also change. So we won't have a line. We will have a curve. And so even here the hydraulic gradient is not constant, so inside the unsaturated zone we shouldn't have a constant hydraulic, but we can assume it is constant approximately. Okay, so this is one point. Hydraulic gradient is constant, so this is not because of the hydraulic gradient. Okay, we should go to another things. When we come from down to the high, what is it changing in the soil? We have a water table here. This point with this point, what is it different? Depth is one of them. I don't talking about depth. What other things? Water content. Pressure, yes, pressure also. Metric potential. And what?
Soil profile also changes.
No, soil, we consider the soil homogeneous. We don't want to make it hard to be heterogeneous. We assume that the soil is homogeneous. So when we go from down to the up, the water content will be different. I showed you the curve. Yes, you can see the water content decrease. When the water content decrease, the unsaturated hydraulic conductivity will decrease. Do you know unsaturated hydraulic conductivity? We have saturated hydraulic conductivity and unsaturated hydraulic conductivity. Have you heard about unsaturated hydraulic conductivity? Even when the water, when the soil is not saturated, again, through the water, in the capillary fringe, for example, we have 70% water, and if we assume that in saturated condition, 100% of the pores are full of water. In capillary fringe, let's say 80% of them are full of water and 20% is empty, but they are connected to each other. This is why we have the movement. So we have hydraulic conductivity even in the capillary fringe, but it is less than the capillary hydraulic conductivity in the saturated zone. When we go from down to the high, then this hydraulic, the water content decrease, so the unsaturated hydraulic conductivity will decrease when we go upward to the high. When hydraulic conductivity decreases, so the velocity will decrease. Why? Because V equals K multiply I. Yes? If K decrease, if hydraulic conductivity is constant, then V decreases. If this K decrease, then V decrease, because I, we assume that it is constant. So when we go from down from the groundwater table, we come higher and higher and higher, the velocity will decrease because the unsaturated hydraulic conductivity decreases. If it is not clear, ask me. And I am showing also here, then it's more. This is the relation for unsaturated, this is a theoretical relation for unsaturated hydraulic conductivity. I don't talk about other parts, I am only talking about this theta. Theta is water content. From this you can understand that if the water content decreases, the unsaturated hydraulic conductivity decreases. So is it completely clear? I didn't talk about this, I will talk about it later. I am only talking that unsaturated hydraulic conductivity will decrease when the water content decreases. And of course, when we are going from water table higher and higher, the unsaturated hydraulic conductivity will decreases. Is it clear? Okay. So we had the experimental data. Now we want to see if the present theories can consider this or not, can predict it or not. For that, we get this formula. Do you know what is this formula? This is Wangen-Ochten formula for water content. Wangen-Ochten. This is a theoretical formula that Wangen-Ochten for the first time described it, and nowadays most models use this model for modeling how is the water content in the vadose zone. They can predict. With this you can predict the water content in different depths, how they change. But you need to calibrate it again, and you should calculate alpha, m, and n with the aid of your experimental results. After that you have alpha, m, and n, then you can put it in the models. For example, if you open any numerical model for groundwater system, at first you should define this formula for it. If you are modeling Richard's equation, if you are going to model the water in the vadose zone, then you should choose which model you want to use for calculating water distribution inside the vadose zone. One of these equations is Wangen-Ochten. We have other question, other formula you can choose, and even you can give your data. If you have a data and you know a function, you can define the function. It depends on the numerical model. Some of the models give you this response, gives freedom that you define your equation for this shape of the formula, because it is necessary to calculate this part. After one, when you calculate alpha, m, and n, you have then m, and this is the theta water content that you can calculate again from this. So you can calculate the K, unsaturated hydraulic conductivity. When you have the unsaturated hydraulic conductivity, you can calculate the velocity in different depths. And we did it, and we see the result. It fit more or less good. No, sorry, this is not this one. This is this black line. This is this equation that I have here is this black line. This is based on Muallim assumption, because in Muallim assumption this L is considered 0.5, and this cos 0 is considered as saturated hydraulic conductivity. Muallim assumed that this cos 0 is saturated hydraulic conductivity, and this L is 0.5, and this is the curve. The other curve that is fit very well, we understood from this curve that the Muallim assumption is not a necessarily good assumption. So we let the model calculate the K and L itself, not the model. We calculate the K and L itself in the Excel with optimization, and we optimize the K, 0, and L to find the best one, and we saw that it's completely fit to the data, and it can see better. And the optimized K, 0, and L, I didn't bring it here, and unfortunately I can check in my data and say, but I am not memorized it. So we don't say so much on the, because it is not our main topic. I wanted to have only a view of our what is other factors that can affect the solute transport, and in some cases it is necessary. For example, capillary fringe is very important when you have a pulse injection. If you have always you have injection, so much injection, maybe the capillary fringe is not important. But if you irrigate half an hour, and then if it rains 10 minutes or half an hour and it stops, then the capillary fringe becomes very important, because the water start to move here, and when it reaches here, the rain is finished, so it is stopped. So we don't have any recharge. So it start to move horizontally. So it never reaches to the groundwater. sorry, it comes to here and it starts horizontally and it never reaches to the groundwater. It goes forward, and all that results change. So we should consider it when modeling the such a things. Another factors that can affect the solute transport is the groundwater surface water interaction. This is another experiment. We wanted to see how is the effect of the distance of the farms from the river to the transported solute to the rivers and to the groundwater. And this is a new technique that we used. We change a little bit the experimental setup, then we can measure the discharge into the river and into the groundwater separately. We add a L part here, you see this L part, and then when the pollutant comes here, the water which comes to this river, we have an outlet for this river. So we can get the outlet from river separately from the groundwater. Because the groundwater comes here and there is a L part here, this is plexiglass. So it makes separate the groundwater and the river from each other. So when the water comes to the river, it comes from another pipe, this red pipe. This red pipes bring out, and the water which comes to the groundwater table from the black one comes out. So we have two different outlets, one for groundwater and one for surface water. Therefore, we can measure the pollutant transport, the amount of the pollutant which comes to the river separately with the groundwater. And if we inject from different part, we can see the effect of the distance on the soluted transport to the river and groundwater separately. So the result of this experiment showed that groundwater surface water interaction also is important, because I didn't bring all the data, but we had also some experiments that we changed the material of this, because in this experiment we assumed that the bed materials in groundwater and the surface water are the same, but it is not in real. In the real, usually in the river we have fine materials, and then the hydraulic conductivity is very low, so it affects the result. So in the second part of the experiment, we changed the bed material of the river to see what happens, and it changed because less pollutant will come into the river, because it is a clay layer, and this clay layer don't let the materials come from the groundwater to the surface water. This is the result of the experiment. This is in this graph we will see the discharge in different times from the river flow and also from the groundwater. And these different colors show injection from different parts. I think I should change this graph because the legends are not in this graph. I should add the legends again before giving the slides to you to understand. Then you will see that when we start to injection in the river at first, in this time, because it doesn't get reach to the river yet, and after a while, it's interesting that the discharge in the river decreases, but the discharge in the groundwater increases. It is because of the water that comes from higher, it puts more pressure, and the discharge of the groundwater will increase, but the discharge of river will decrease. And here, because it's going higher, because we stop injection. When we stop injection, again the discharge going higher. This is the total discharge. You see that it is almost constant. But the main data that we want to see is this one, which is related to the change in the electrical conductivity. We measured the electrical conductivity in the outlet of the river and in the outlet of the groundwater to see how it changed. As you can see here, the when we inject, this is the EC change again in the river, and this is the EC change in the groundwater. You can see that in the groundwater, when this one is when it is more closer. When it is more close, you can see the result faster, and it stay less than when it is farther. It's because it is the effect of dispersion coefficient. Yes, because you see when the green one is the injection from a farthest farm, the farm which is farther than the river. So when it is farther, then the length is more. So it shows that it stay more in the groundwater. But when it is closer, then it is smaller. Another point, you can see that here is also the same in the river. Also, when it is farther, then it is. And another point is that the difference between the distance in the groundwater is much more clear than the river. Okay. Okay, we can have some rest and lunch, and after that we continue to how to model with MATLAB. Do you have any question? If you have any question before leaving, we can. There is no question.